Gross geometry. This video series talks about the more wordy side of geometry, and let's get started with a bunch of dots. What conjecture can you make about the number of dots in the nth term? Now, conjecture is like, what true statement or fact can you make about what's going on here? Well, one term is one dot. Great. Two terms is 5. So 1 becomes 1, 2 becomes 5, 3 becomes, what is that, 11? Ugh, that's a terrible band. And 4 becomes 19. So what I immediately see is with 2, 3, and 4, it looks like I have 2 squared living here and I add 1. 3 squared, add 2. 4 squared, add 3. So that's how I'm going to approach it. I'm going to think my number term squared, and then I'm going to add the number less than that. So the way that we would show that is we would say plus n minus 1. But in order for that to be true, it has to be true for all. I didn't test that with 1 because, I can't really see that well with 1 as far as what I'm doing. But, if I do 2, it is 2 squared, 4, plus 2 minus 1, which is 1. So that works. So it works for you. 3 squared plus 2, 4 squared plus 3. This would be 1 squared plus 1 minus 1, which becomes 1 plus 0. So it does work. So we found our conjecture. So let's put this in a nice little statement. What conjecture can you make of the number of dots? There are n squared plus n minus 1 dots in the nth term. We'll write that there because I ran out of space. But yeah, that's what a conjecture means in this case. So this required us to think a little bit harder, and we did, and we got it right. Good job, everybody. Statement. All rectangles are squares. Provide a counterexample proving this statement is false. What is a counterexample? Well, a counterexample is a statement, a sentence that shows you and proves you that this statement is not 100% true. Okay, so like if I were to say, all cool guys are 23 years old, that's not true because I'm cool and I'm 28. So how can we do that here? How can we provide a counterexample for all rectangles are squares? Well, that's not true because some rectangles have sides that are not, there's an S there, all the same. For example, this guy, if I can draw correctly, is a rectangle. And these two guys are the same. These two guys are the same. That's a rectangle, but it's not a square. So basically, when you see a statement that says all or every or something like that, you're looking for a reason why that all or every is not true, and that's what a counterexample does. It shows you the lies, just like social media. Show that each conjecture is either true or false. So, all right, so I've got 2 statements here, and I need to show if the statement is a correct statement or not a correct statement. The sum of 2 even numbers is always even. So let's try a few out. 2 even numbers. 2 plus 6 is 8, even, check. 10 plus 16 equals 26, even, check. How about 2 plus negative 2 is 0, which is technically even, check. So it looks like no matter what 2 even numbers I add, it's going to be even no matter what. So is this a true statement? Yes, it is. That's a cat. Now, the product of two negative numbers is always negative. Is that true or false? Well, let's multiply two negative numbers together. Negative 3 times negative 4 is positive 12. Well, here it says the product of two negative numbers is always negative. Well, immediately I try one of them and it's false. So is this true? No, this is false. This says up here true or false, and I'm saying yes or no. I just wanted to say yes because I like saying yes. Like and subscribe. Identify the hypothesis and the conclusion of the conditional statement. A conditional statement says, if blah, 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 then blah, blah, blah. It could also be written like this, P then Q, where P is your hypothesis and Q is your conclusion. If P, then Q. This is already written to us as an if-then statement. So, fairly simple. The hypothesis is going to be the phrase after the if. So if a cat hears a cat opener or a can opener, I don't want to know what a cat opener is. If a cat hears a can opener, the conclusion is going to be the phrase following then. So then it will come running to the kitchen. So conclusion, it will come running to the kitchen. Okay? So conditional statement, if blah, then blah. After if is the hypothesis, after then is the conclusion. And it sure is easier when it's already written to us as a conditional statement like this one here. Cats. Write the following as a conditional statement. All right, a conditional statement is in this form, P then Q, which means if some type of hypothesis happens, then the conclusion. Okay, so if one thing, then the other. A plant will grow taller when it is watered properly. Now, we have to be careful here because we're not going to say if a plant will grow taller, then it is watered properly. That doesn't sound right. This is backwards. So our hypothesis is if a plant is watered properly. And again, the wording can be a little different, but since we're talking about plants, I want to make sure that I bring up the plant stuff first, then Q, then it will grow taller. Okay, so let's write that out. If a plant is watered properly, comma, and let's change colors, then it will grow taller. What's important with these is this is just how I'm writing it out. You may have a teacher, or you may have a friend, or you may have a deity that might write it out differently. But, this is how I'm wording it. And don't let the little words like, where should I put the word plant? You forgot to say the word when, why, blah, 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 blah. Don't worry about it. I'm just writing it out in a way that makes it sound like it makes sense. And the hypothesis comes first and the conclusion comes second. That's it. Write each. If a cat sees a laser pointer dot moving, then it will chase it. All right, so we have ourselves a conditional statement, which is in the form if P, then Q. P is my hypothesis. If a cat sees a laser point dot moving, that is P. It will chase it is my Q. What I have to do is turn all of these into the converse, the negation, the inverse, and the contrapositive. So let's start out with the converse, which is a brand of shoes. A converse says, let's just switch the Q into P. If Q, then P. We'll write that out in a little bit. Negation has you do P, then not Q. The inverse has you take the original but put knots in front of both of them. Speaking of converse, knots. And the contrapositive is you flip everything and make everything negative. So not Q implies not P. So let's do a little bit of writing. Converse. If a cat will chase it, then a laser pointer dot is moving. So I hate the way that that's worded, but that's it. If a cat, and let's actually be a little bit more specific. If a cat chases a laser pointer dot, if a cat chases a laser pointer dot, then it is moving. So what you saw me do here is I moved some words around to make the sentence make sense. If I were just to go in reverse and say, if it will chase it, then a cat sees a laser pointer dot moving. That's not wrong, but this just sounds better. If a cat chases a laser pointer dot, then it is moving. I'm kind of happy with that. Let's keep going though. Negation. So the first part doesn't change. If a cat sees a laser pointer dot moving, okay, so the first part didn't change at all, word for word, then it will not chase it. Then it will not chase it. So that's what that little squiggly means. That means we're going to take Q and make it a false statement or make it a not. There you have it. Inverse is we're going to write out the same thing but throw a not here and a not here. Oh, speaking of cats, one just walked into the room that I'm recording in. So hello, little kitten. No, please. I swear there's a cat here. All right. If a cat does not see a laser pointer dot moving, if a cat does not see a laser pointer dot moving, then it will not chase it. Okay? So P, thank you, not. Last but not least, we have our contrapositive, which is basically you rewrite out Q but throw nots in front of both of those. So if a cat does not chase a laser pointer dot, then it is not moving. So as you can see, these aren't fun. And the purpose of these videos or this series of videos, gross geometry, is there's really no math here at all. You're just making logical statements which will lead into something called proofs, where you need to know a whole lot about logic and reasoning and all that stuff. And isn't that life? Cats and logic. That'll probably be the name of my memoir. Like and subscribe. Create a truth table for the conditional statement. If the Spartans win one more game, they will make the playoffs. So a truth table has you have your hypothesis, your conclusion, and then whether it's true or false based off of what you say. So there's only going to be 4 options here. Okay, both situations are true. The hypothesis is true, but the conclusion is false. The hypothesis is false and the conclusion is true. And if the hypothesis is false, then the conclusion is false. So when we look at this, we're going to view this from this real life fake problem that I just made. The Spartans win one more game is P. They will make the playoffs is going to be Q. So if the Spartans win one more game, they will make the playoffs. If the Spartans win one more game, they will make the playoffs. True. That's the original statement. So that would make sense that if P then Q, then P then Q is true. All right. If P is true and Q is false, if the Spartans win one more game, then they will not make the playoffs. Well, that is a lie given the original statement. If the Spartans win one more game, they will make the playoffs. So if someone were to come up to me and say, if the Spartans win one more game, they will not make the playoffs. Well, that's not true, according to this statement here. If the Spartans win one more game, no. If the Spartans win one more game, oh my gosh. If the Spartans do not win one more game, then they will make the playoffs. So basically, they can win no more games. They can win 2 more games. They can win 3 more games. They can win 4 more games. It all really depends. But since we are not given all the information, and I'm telling you right now that it's true that they will make the playoffs, then this statement is true, whether they win 1, 2, 3, 4, 0, whatever. If I'm running up to you and say the Spartans will make the playoffs, then it's true. Okay. So last but not least, true or false, if the Spartans do not win one more game, then they will not make the playoffs. That is a true statement. Okay? So there you have it. True, 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 true. I'm just repeating a Master P song from the early 2000s called True. Look it up. Just not in front of your parents. Lots of bad words. Write the biconditional statement for if lines intersect at 4 right angles, then the lines are perpendicular. Biconditional statements are if and only if statements. Okay, so I have children, and if my children are like, Dad, can we watch television? And if I were like, yeah, but only if you do your chores, then my children can watch television if and only if they do their chores. Well, lines intersect at 4 right angles. If that happens, then the lines are perpendicular. Okay, well, here's my if. So that's actually going to be my second part of the sentence. My first part of the sentence is lines are perpendicular if and only if they intersect at 4 right angles. So I know it sounds kind of backwardsy, but it all depends on if one depends on the other. Use the word depend a lot. But that's how this one works out. You got to kind of switch the words around a little bit, but I threw the if and only if. By the way, some teachers use this for if and only if, and if you're like, oh, that teacher doesn't know how to spell. No, a lot of teachers use that for if and only if. But those are biconditional statements. If. Law of detachment is one of those really weird rules. Basically, if I tell you that if P then Q is a true statement and P is true, then Q is true. Now, that's usually used when you have problems like this where not everything is as clear-cut as it could be, and so you're kind of going like, oh, we have to use logic now. That's what the law of detachment is. It's just logic. If Alicia scores 85 or greater on her test, she will earn an A on her final grade. Terrific. Alicia scores 89 on her test. What can you logically conclude? Well, if she scores 85 or higher, she gets an A. What did she score? 89? Oh, well then what can we conclude? She will earn an A, make it a big A, as her final grade. So law of detachment, kind of stupid. That's why this is called gross geometry, because gross geometry is kind of stupid, but, logical. So there you have it. The law of syllogism. There's nothing funny about the law of syllogism. Law of syllogism says if P then Q, and then Q then R, then P then R. Skips out the middleman. All right. If I am cool and if someone is cool deserves you to like and subscribe to my channel, then I deserve for you to like and subscribe to my channel. Law of syllogism. If it rains, then the ground gets wet. Neat. If the ground gets wet, then the grass becomes green. Neat. Using the law of syllogism, what can you conclude? Well, if it rains, that's P. Q is going to be the ground gets wet. The second statement starts out with if the ground gets wet. So what we're going to do is cut out the middleman and go right from P to R. If it rains, then the grass becomes green. If it rains, then the grass becomes green. And look at that. I chose a green pen just for this. I did it on purpose. All right, so this is the end of part 1 of gross geometry, where we aren't really doing a whole lot of math. We're doing a lot of logic. And logic is required for stuff that we will deal with called proofs, and that'll be the next volume of my gross geometry series. Thanks for watching.